Okay. All right, guys. So we talked about last class molecular polarity, and we talked about intermolecular forces. So this slide here is a picture of hemoglobin. So one of the reasons why understanding intermolecular forces is so important is because a lot of the way that big organic molecules function is completely dictated by how they arrange three-dimensionally, and that arrangement three-dimensionally has everything to do with these intermolecular forces. So it's all about the areas that are polar being attracted to other polar areas, and the areas that are non-polar being repelled by the polar areas, etc. Right? So this is hemoglobin. This is what transfers oxygen in our blood. And again, if you have very small errors in the RNA that is responsible for making this protein, the structure will not have this kind of three-dimensional arrangement, and then its functionality can completely be lost by that. So are any of you guys familiar with sickle cell anemia?
Yeah.
Yeah, so that's one of the ways where having these proteins be malformed can make it so that your blood does not transport oxygen properly, right? So definitely this part of understanding intermolecular forces is tremendously important, especially if you're going into any kind of biological fields. Okay, so we talked about last class the difference between intramolecular forces and intermolecular forces. So intra meaning within is the glue that holds the molecules together. These would be covalent sigma bonds, covalent pi bonds, and electrostatic or ionic bonds. Intermolecular, inter meaning between, is like the Velcro that sticks molecules together to make condensed phases, right? Intramolecular are much, much stronger than intermolecular. Questions about that? So those are definitions you should definitely be familiar with for an exam. Cool?
Yeah.
Okay, so there's 4 basic flavors of intermolecular forces. And occasionally textbooks will only include 3, but whoops, our textbook I think includes all 4 of them. The strongest one being the ion-dipole interactions, the next strongest being the dipole-dipole interactions. And we talked about the dipole-dipole interactions that are the strongest are hydrogen bonds, right? So technically the order of strength would be ion-dipole, then hydrogen bonds, then general dipole-dipole, and then the weakest would be dispersion or London forces, right? The stronger the attractive forces among particles, the more they resist moving, right? So when we think about molecular freedom now, what we really want to think about is how much energy does it take to get these molecules to move away from each other, right? So these attractive forces are essentially making molecules resistant to moving. Does that make sense, guys?
Yeah.
Cool. So less particle freedom of movement, the more condensed the phase, right? Particles with high kinetic energies will experience less attractive forces than molecules in condensed phases, right? So what does that mean? High kinetic energy. So what are we talking about with kinetic energy?
Movement of the particles in a container.
What, Angelique? Sorry.
Oh, movement of particles.
Yeah, exactly. We're talking about movement of particles. So kinetic energy meaning the ability to move, right? Lower kinetic energy meaning less ability to move. So ion dipole, this is a picture I think we talked about in chapter 4 as well, right? So the polarity of water and the ion charges allow this attraction where you get a solvation shell around the ions that essentially comfort the ions and allow them to be incorporated into the water in a solution. The strength of the ion dipole attraction is one of the main factors that determines the solubility of an ionic compound. So chapter 11 is all about solutions. So this idea of intermolecular forces and ion solvent attraction is going to be really important going into chapter 11, okay? Any questions about those? All right. Okay, so I think we talked about that in detail, but there's some nice pretty pictures of water breaking down ionic salts. Now we're looking at the dipole-dipole interactions. So these electrostatic potential maps, these guys, I think make it a lot easier to kind of see what we're talking about in terms of these molecular dipoles. So this blue area is a lack of electron density, and the red area is extra electron density, right? So when we're talking about a molecular dipole, it's really about where electrons are in the entire molecule, or where they aren't, as it were. Does that make sense, guys? Is that a helpful picture? A little bit better than maybe my drawings?
They're both equally good.
You're sweet, Maya. That's not true. Cool. But again, one of the things that's necessary in order to have these dipole-dipole interactions is a permanent, aka net dipole on the molecule. So it means that the molecule must be polar. And in order to be polar, you must have polar bonds and be asymmetric. The more polar a molecule is, the more attracted they will be, the stronger these dipole-dipole interactions will be. So when we're looking at this attraction and meaning less freedom of movement for particles, more polar molecules will have relatively higher melting and boiling points, right? So thinking about what you know about water, for example, right? What's the boiling point of water? Don't all answer at once. Nobody?
Yeah, I don't know.
The boiling point of water?
100?
100 degrees Celsius. You knew that, Teddy. You knew that. 100 degrees Celsius, right? What do you know about alcohols? Do they boil at lower or higher temperatures than water?
I'm
Guess
lower.
H bonding.
They boil at lower temperatures, right? So for example, if you were to leave a bottle of vodka open versus a bottle of water, which one would evaporate more quickly?
The vodka.
The vodka, yeah, unfortunately. But the reason for that is because water has stronger intermolecular forces than the alcohol does, right? And we can look at some examples of that specifically, right? But that's what we're thinking about when we're trying to understand these intermolecular forces, right? So the stronger they are, the harder it is to get the molecules apart, the higher the melting, the boiling points, and the temperature of evaporation, right? Or the rate of evaporation, which is what we're going to talk about next. Does that make sense, guys?
Yeah.
Yeah.
Cool. All right. So then we have the specific, very strong version of these dipole-dipole interactions, which are called hydrogen bonds. And again, those only occur when you have oxygen bonded to hydrogen, nitrogen bonded to hydrogen, or fluorine bonded to hydrogen, right? So you have to have those bonds and those atoms directly attached to each other not just in the molecule, right? So you could have oxygen and hydrogen in the same molecule and not have hydrogen bonding, right? You guys remember that?
Yeah.
Cool. And again, we talked about the reason why these are so strong is because hydrogen only has that one electron, and when it's being pulled really hard by nitrogen, fluorine, and oxygen, who are all extremely electronegative, it essentially exposes that proton, right? So it acts as a very strong positive charge, which allows for more attraction from neighboring electron clouds. Does that make sense, guys?
Yeah.
Cool. All right. And I think we talked a little bit about this in terms of the relative strength of covalent bonds versus hydrogen bonds. So hydrogen bonds are about 2 to 5% the strength of a covalent bond. So they're significantly less strong, but they're still strong enough to have a really crucial role in forming secondary and tertiary structures in things like proteins and enzymes. So in terms of large organic molecules, they are probably the most important thing, right? And then we talked about London or dispersion forces. So we said that there's small fluctuations that can happen in terms of the electron positions from moment to moment. And we can have this temporary dipole created by the natural fluctuations in electrons. It's not necessarily the most energetically favorable configuration of electrons, and that's why it's temporary, but it is a possible way to have electrons congregate in one part of a molecule or atom to set up this temporary dipole. It's the weakest because it's so temporary, and the only time that you end up having this induced dipole where it's more than temporary is usually under conditions of higher densities and higher pressures, right? When you're forcing these molecules to interact. Does that make sense?
Yeah.
Cool. Any questions about the intermolecular forces? You guys pretty comfortable with those?
Yes.
For the most part, yeah.
Cool. So one of the other things that's going to affect the strength of dispersion forces in molecules is size or mass, right? Did we talk about this? Did we talk about molar mass? No?
Not
Um,
referring to
That was
the
my other class. Okay. So, so when you're talking about the strength of these instantaneous dipoles or the strength of the dispersion forces that are involved between particles, the bigger the molecule is, or the bigger the atom is, the more polarizable the electrons, which is a fancy way of saying that the electrons are basically more free out here. They're not being pulled on as hard by that positively charged nucleus, right? So the electrons are able to move more in the valence than they would in something smaller that has a really strong pull from that positively charged nucleus on the outer electrons. Does that make sense, guys?
Yeah.
So if you were, well, okay, so you guys can see this, sorry, part of my screen is blocked off by you guys, but you guys can see here clearly in the boiling points of the noble gases that as you go down the periodic table, what happens to the boiling point?
It gets higher.
It gets higher, so what does that mean?
The molar mass. Well, there's a direct relationship between molar mass and boiling point.
Right, but in terms of the intermolecular forces, what's happening as you go down the periodic table?
More movement, ability of movement in the bigger molecules.
But specifically, we're talking about the attraction between particles. Is there more attraction or less attraction?
More.
More, absolutely, right? So does that make sense, guys? So when we're talking about dispersion forces, we can see that dispersion forces will increase in strength with the increase in mass, right? Does that kind of make sense?
Yeah.
Cool. So one of the good examples that you guys can think about, not because more protons, Harrison, but because you have your radius is larger as you go down the periodic table, and the distance between the valence electrons and that positively charged core is bigger. So thinking about that electrostatic attraction, right? Coulomb's law, the two charges multiplied together divided by R, right? So you're essentially making R bigger and bigger as you go down the periodic table. So that allows those outermost electrons to be more mobile because they're not being held on to as tightly by the positively charged nucleus. Does that make sense? Got it, cool. So we can actually see this directly in terms of the phases of the diatomics, right? So if we were looking at the halogens, for example, fluorine, chlorine, bromine, and iodine, the first two are gases, fluorine and chlorine. Bromine, what phase is bromine?
Liquid.
Liquid. And what about iodine?
Liquid.
Solid. Sorry. You guys see that? So the red means gas, the blue means liquid, and the black means solid, right? So thinking about those halogens as we go down the periodic table, they increase in size dramatically, right? As they increase in size, the amount of intermolecular attraction between those particles also increases, which makes them more likely to form condensed phases, even though they're nonpolar. Does that make sense?
Yeah.
Questions about that? That's going to be real important. We're okay? All right. Cool. So larger molar mass, more electrons, larger electron clouds, increased polarizability, stronger attractions, right? So that's how you can think about these molar mass relationship between the attractions. And we know that the stronger the attractions, the higher the melting or the boiling points will be of that substance, right? That's also a really important thing to know. Cool. Cool. The other thing that's going to play into this is the shape of the molecules, right? So the more surface-to-surface contact you have, the more intermolecular forces or attractions you'll have. So rounder molecules are less interacting with each other than flatter molecules. So more surface-to-surface contact, larger induced dipoles, stronger attractions. And we'll look at some examples of that down the line. Questions? Coolsies. All right, so this is what we were talking about before with ethanol, right? So looking at ethanol, right? This is the molecule for ethanol. And you can see there's this area that's clearly polar, right? So we have this area of very low electron density and much higher electron density, right? But the strength of this dipole is nothing compared to water, right? And that's why ethanol evaporates so much more quickly, because its molecules are not as attracted to each other as water is to itself. Does that make sense, guys?
Yeah.
Cool. Thank you, Harrison. Okay, so looking at each one of these molecules, ethanol has what kind of intermolecular forces?
Hydrogen
Oh.
bonding?
What's the strongest? We'll put it that way.
Oh.
Somebody said something. What?
Well, I said hydrogen bonding, but I don't think that's the strongest.
It is
Oh,
actually,
it is. Okay.
right?
Trying to
So-
see if it was polar. I'm like,
So it is polar, right? And you have oxygen bonded to hydrogen directly, right? So this has hydrogen bonding. Does that make sense, guys?
Yeah.
Cool. What about propane? It's the strongest intermolecular force in propane.
is it just London dispersion?
Yep, dispersion forces, absolutely. Is everybody comfortable with that?
Yeah.
Cool. And what about this last one, acetone? What's the strongest intermolecular force there?
Would it be dipole?
It is dipole-dipole, right? So this is an example where you have oxygen and hydrogen in a molecule, but you don't have oxygen directly attached to hydrogen, right? So you don't have hydrogen bonding, but you do have a dipole, right? A net dipole on the molecule. That makes sense, guys?
Yes.
Cool. It's definitely something you'll see on an exam or a quiz. So looking at condensed phases in terms of solubility. So solubility depends in part on the attractive forces between the solute and the solvent molecules. We have this rule of thumb where we say like dissolves like. So miscible liquids will always dissolve in each other. A polar substance likes to dissolve in polar solvents. And nonpolar molecules like to dissolve in nonpolar solvents, right? So when you have a polar group, we call this hydrophilic, hydro meaning water, and philic meaning love of, right? So hydrophilic groups love water. But a lot of the times in organic compounds, you'll have both hydrophilic and hydrophobic groups. Hydrophobic meaning fear of water, right? So hydrophobic groups want nothing to do with water. Because these molecules often have both parts, the solubility in water becomes a competition between the attraction of the polar groups for the water and the repulsion of the nonpolar groups by the water, right? And so a lot of that plays into this secondary and tertiary structure of big, complicated organic molecules. Coolsies. And we're going to talk a lot more about solubility next chapter too. So for example, pentane, which is a nonpolar molecule, does not have a dipole, only has dispersion forces, right? It does not want to hang out with water, which is a very polar molecule, right? So when you have liquids that won't mix together, we call them immiscible. You guys are familiar with that, I think, from lab too.
I have a question.
Yes.
Do you want us to know like what would be the top layer and bottom layer, or is that completely going too far? Like in a compound or in a solution?
So generally speaking, you will eventually need to know that kind of stuff. But it's a pretty safe bet that organic molecules, and you'll learn more about this when you work with them in organic chemistry, organic molecules are oily, and oily things tend to have lower densities than water. One of the reasons why water has such a high density is because it has such strong intermolecular attractions, right?
Okay, so is it just a general rule of thumb, like if you have more polar molecule, then it would have a higher density, or?
Generally speaking, yes.
Okay.
That's probably a trend that you could find a lot of exceptions